Welcome to the R Lab for PCA and clustering. We're going to start by walking through some principal components analysis for the US arrests dataset. And so we begin by looking at the states, which are the row names for this dataset. And we can look at the row names. Down here we see the row names correspond to the United States in alphabetical order. We can take another look at the datasets, and we use the names command on the datasets. That gives us the names of the feature variables, and there are murder, assault, urban population, which is the percent living in urban population of rape, and for the crimes, the 3 crimes there, the values there are the number of individuals committing those crimes per 100,000 people in the state. We can compute the mean for each of those, and this apply command that we used right here applies the mean function to this too, says apply it to the rows of that data set. And so we see these different features have different means. Rape occurs 3 times more often than murder, and assault 5, 6, 7, 8 or so times more common than rape. And then urban population, we can see the average value there. We can also look at the variance for these, and the variance for assault is the largest. And so we can see that these variables are on very different scales from each other. We could apply the principal components now to this data set, and when we put in here, we're using the PRComp command, and that's the principal components command built into R. To this data set, scale equals true tells the command that we're going to scale each variable by its mean and standard deviation, so make it have mean 0 and standard deviation 1 before computing the principal components analysis. And then we can look at the names that are in principal components analysis out. And so we have standard deviation, we have the rotation, which gives us the information on the rotation from the original feature variables to the PCA variables, and other information about the data. And so we could look at the PR out center and the scale for these. And so this tells us first how far these were transferred, how much they were moved when they were centered, and then the scale, how much they were scaled when we did the standard deviation scaling. And then the rotation is the matrix that was used to rotate the data, which has as columns the principal components, the individual principal components. And so here's principal component 1, and these values are the loadings of that principal component, or the components of that principal component as a vector. And so we can see PC1 points strongly in directions of the crimes, but not the urban population as much, and PC2 points more strongly in the direction of urban population. Of course, the dimensions of PR out, it has 50 rows and 4 columns, the same as the original data. And now we can plot, or create what's called a biplot in R of the PR out. And so this is similar to a figure from the textbook and from lesson videos. And you can see the urban populations pointing down and these to the left. This may look nicer if the urban population was pointing up and these to the right, that we've seen a similar plot, but reversed that way. And that's because the principal components are unique up to direction. So PC1 might point directly to the right 1 unit or directly to the left 1 unit. And so we can rotate this by just taking the rotation and setting equal to the negative rotation. So that'll multiply every principal component vector by a -1. And then we can create a biplot with that. And now we can see our principal components plot. And we can see states pointing more towards the right have higher crime directions, and the states pointing more up are higher urban population. And then we could get some more information about the principal components here, and now we are going to compute the amount of information contained in each principal component, which is equal to the variance in the direction of that principal component. So PR_var, we've set that equal to PR_out and taken the standard deviation out of that PR_out structure and then squared it to get the variance. And so here's the variance in the direction of each of those principal components. In PV, it's the PV variance. It's these variances divided by the sum of the variances. And so PVE is going to give us the proportion of variance contained in each of those four principal components. So the first PC has 62% of the variance, or 62% of the information. The second one has 24% of the variance. And then these third and fourth don't have much of the information. And we can plot these proportions of variance. So this plot shows us on the vertical axis the proportional variance for that single principal component, and the horizontal axis is the number for the principal component. We can also plot the cumulative variance. So if we just use the first principal component to approximate the data, we're getting 62% of the variance. But if we use the first two together, we get 88 or so percent of the variance or the information. So using those first two principal components, we can trust that we have a decent picture of what's going on in the data. Just to demonstrate what this cumulative sum command does, it's going to take the proportion of variance here and then take the cumulative sum as you go across. So this cumulative sum of 1, 2, 8, and 3, this is the sum of 1, this is the sum of 1 and 2, this is the sum of 1 and 2 and 8, and this is the sum of 1 and 2 and 8 and -3. So it sums that vector cumulatively left to right. Okay, so now we're going to look at some clustering. First, we'll walk through some k-means clustering. We're going to set our seed. Then we're going to generate some data. So X is going to be a matrix. It's going to be a random normal variable with 2 columns and 50 observations. And we're going to shift the first 25 of those +3 and -4 so that we separate these out. So the first 25 represent one class, and the second 25 represent what would be a second class. So there's something different in the locations between the first 25 and the second. And now we've run k-means. The command in R to run k-means is conveniently enough, appropriately enough, k-means. Here's our data. We're going to do 2 means, and we execute our k-means, and now we can look at the clusters that have been assigned, and k-means did a good job. The first 25 points have been assigned to cluster 1, and the next 25 points have been assigned to cluster 2. We can plot this. So we're plotting X, then coloring the points by their cluster designation, and then setting up our title and our X label and Y label. PCH and CEX give the size and type of markers in that plot. Now we're going to set our seed to 4. Now PCA uses some random generation of initial class labels, so we need to set our seed if we're going to get the same output every time. So now we're going to run k-means, but you'll notice we're doing k equals 3, so we're going to compute 3 classes or 3 clusters. It's appropriate to call these clusters because we're not working off of known class labels. So sometimes people call what I would consider inaccurately called as classifying classes, but they should properly be called clusters. So here are all the variable components that are included in the KMOut, right? That's the output from k-means. And so we're going to plot this using our 3 classes, or 3 clusters, excuse me, there we go. And you'll see we have this green, this blue, and this red. And although the data seems most naturally to split into the 2 clusters that we initially put it in, this 3 clusters isn't a horrible clustering. It makes sense if you're going to separate that data into 3 clusters. Now we can compute some metrics for the quality of the clustering that goes with k-means. And now let's do some hierarchical clustering. So we're going to take that data X and we're going to run hierarchical clustering on it. That's hclust is a command for that. We're going to use the method complete. And so complete compares two classes by taking the farthest distance between pairs of points in those two classes. And so we'll compute hierarchical clustering with complete, and then average, and then single. And now we're going to make a set of plots with 3 rows. We'll plot the complete linkage, average linkage, and then single linkage. And so these are the dendrograms for the 3 different types of linkages. And you can see for the complete linkage, if I were to threshold here, I would get the 2, which are probably the initial 2 groups that we use to generate this data. Average linkage would also do reasonably well. Single linkage tends to get messier, less organized dendrograms that would look like this, and we see it doesn't seem that it would do a perfect job. I'm not quite sure where to cut it, but there doesn't seem a spot that would cut it into 2 groups of the same size. Maybe here and we get 2 groups, but then we get these 2 isolated individual ones. If we cut it up here, we would get 1 group with everything but 1 point, and then 1 group with just 16. So we can cut the tree and then see what we get when we cut the tree. So we can cut the tree for the complete linkage, and we see we get perfect results, 25 1s and 25 2s. For the average linkage, we cut it at the point where we have, this is cutting it where it has 2 branches. We cut it at the height where there's 2 branches, and we get perfect classification. We cut the single linkage tree where it has 2 branches, which is up here. 1 branch has everything, the other branch has just 1 data point in it, and that's where we get everything except for that 1 is called a 1, and then the 2 is in, I think it was, looks like maybe index 16 on that point. We can cut at a level of 4, and we get decent results. Here's the 1s, and there's that 1 standing out point, which has a 2, and then the 3s, and there's a 4 in the midst of those. So better results, but not perfect from that clustering. So this completes our video looking at clustering and PCA. Thank you very much for watching.